Swayamprabha. Digital India. Educated India.
In the previous lecture, we discussed about the energy equation and we derived the energy equation in terms of enthalpy. So, what is the form of the energy equation that we derived in the previous lecture? So, to have a look into this, let us have a recapitulation that let us recapitulate one or two steps before that. So, first we wrote the Reynolds transport equation for the total energy conservation, then the rate of energy change within the system we expressed in terms of the heat transfer and the work done by using the first law of thermodynamics. The heat transfer involved surface heat transfer and volumetric heat transfer. The work done involved the work done due to surface force and work done due to body force, and then in terms of the internal in terms of the total energy we could write an expression for the first law and combine that with the Reynolds transport theorem to get this differential form of the conservation equation. Then we subtracted the mechanical energy conservation equation from this to get the internal energy, the governing equation in terms of the internal energy, and then in that equation we simplified a term which is because of viscous heating, because of energy dissipation due to work done against the viscous stresses, and once we calculated that, we figured out that viscous dissipation term that is given by mu phi in this expression is always going to be positive. So, with this and transferring the internal energy to enthalpy, we have got the governing equation in this form. This is the form that I think this is the last form that we derived in the previous lecture before we concluded the previous lecture, that rho total derivative of H minus total derivative of P is equal to the heat generation per unit volume minus the gradient of the heat flux vector and plus mu phi, which is the viscous dissipation term. Now, we have to appreciate that in the energy equation we are interested eventually in terms of to express everything in terms of the variation in temperature, because temperature is the variable that is directly measurable from experimental considerations, and we have a particular physical appeal to temperature. Very intuitively that kind of physical appeal is not existing for enthalpy or internal energy, these types of variables. So, our next objective will be to express the expression in terms of enthalpy in terms of temperature and pressure. So, that is what we will do. Now, to do that we require certain thermodynamic basis. I presume that all of you have the thermodynamic basis, but we will discuss in very brief about the concepts that we will be talking about when we go through the necessary steps. So, if you have, for example, H is the enthalpy. H is a function of what? H is a function of two independent intensive thermodynamic properties, provided the substance is a simple compressible pure substance. A simple compressible pure substance you all of you understand what is a pure substance. So, a pure substance is a chemically homogeneous substance. Now, what is a simple compressible substance? A simple compressible substance is a substance where the changes in pressure, volume, temperature, these effects are much more important than the other effects, for example electrical, magnetic and all any other physical effect. So, we are expressing H as a function of say T and P. We could also express it in terms of some magnetization, electrical field, all these things, but those effects are not important because we are considering it as a simple compressible substance. And the implicit thing here is that this is what is nothing but in thermodynamics called as state postulate, that the state of a thermodynamic substance can be expressed in terms of two independent intensive thermodynamic properties. Now, the question is, where is the guarantee that T and P are independent? Can you give the example of a situation when T and P are dependent, like phase transformation? For example, let us say you are talking about melting of ice, for example. So, if you have a pure substance changing its phase, in fact the phase changing temperature is a single valued function of the phase changing pressure. So, once you specify the phase changing pressure, the phase changing temperature will be automatically specified. So, that means we are assuming here implicitly that there is no phase change, although we are not writing it somewhere. So, no phase change. So, this is a convenient way of expressing H, because we have tried to express H in terms of two variables which we can measure in engineering applications. So, dH this is what we can write. This is by the simple rule of partial derivative. Now, what is this? This is by definition Cp. Then what we will do is, see, there are certain variables which we cannot measure directly. For example, I mean variation of enthalpy with pressure. So, there is no measuring device that can directly measure this. So, we will try to express this some variables that can be directly measured. To do that, what we will do is, we will write this in terms of first something which cannot be directly measured, and then express that in terms of other measurable quantities. So, to do that we will use one of the 4 TdS relationships. TdS is equal to dH minus VdP, right. So, I will briefly discuss about the validity of this expression and all. So, to establish this equation, it is very straightforward. We start with del Q is equal to dE plus del W, okay. What is this? This is the first law of thermodynamics for a system undergoing any process, for a control mass system undergoing any process. So, we will start with this. Now, first we will make one assumption after the other, and remember that these assumptions are inbuilt with the derivation of this equation. Again I am repeating that many times there is a tendency that we just plug in a final formula to solve a problem. There is nothing wrong with it, provided we know that what are the assumptions and restrictions under which that final formula is valid. So, that kind of, I mean, as a teacher I always therefore emphasize on knowing the roots by which a final formula has been derived, so that while applying that you know that what are the conditions under which you apply that, rather than taking that as a magic formula to solve a problem for which that formula is not applicable at all. So, see, the first assumption that we will make is that the changes in kinetic energy and potential energy are negligible as compared to the changes in internal energy. So, this is a typical thermal problem, you know, that you have a problem where thermal effects are much more important. So, changes in kinetic energy and potential energy are not that important as compared to the changes in internal energy. So, that instead of dE we can write dI. I stands for internal energy. Okay. The next two assumptions are very critical. The next two assumptions that we are writing is, instead of del Q we will write TdS. Well, the next step we will divide all the terms per unit mass. So, we will write them per unit mass. So, we will write in terms of the specific quantities. In place of del Q we will write TdS, and in place of del W we will write PdV. Okay. So, let us come one by one. So, first question, can we write these always? The answer is straightforward, no, we cannot write this always. So, let us try to assess the situation when we can write this. PdV, when can we write del W as PdV? When we can write del W as PdV when it is a moving boundary in a quasi static or quasi equilibrium process, and only form of work is the moving boundary work. There could be other forms of work, for example electrical work, magnetic work, all those works are not considered, only the moving boundary work is considered, and that also the system is considered to be undergoing a quasi equilibrium or quasi static process. So, the assumption behind PdV is clear. What is the assumption behind TdS? It is a reversible process. So, now when we say it is a reversible process, it also has to be a quasi equilibrium process, but the inverse is not true, you have to keep in mind, because quasi equilibrium process just means that in terms of the internal irreversibility, the internal irreversibilities are not there. So, that because the system is in quasi equilibrium process, what is happening? A system is moving very slowly from one equilibrium state to the other, so that all intermediate states are in thermodynamic equilibrium. So, it is a sort of a very slow process. So, that makes the process internally reversible, but a quasi equilibrium process could be externally reversible. For example, there could be a finite temperature difference for heat transfer between the system and the surrounding, and that will make a process externally irreversible. So, external irreversibility may be there even if it is quasi equilibrium, right. So, for example, the system boundary is at a temperature of 10 degree centigrade and the ambience is at a temperature of 30 degree centigrade. So, because of this finite temperature difference, the heat transfer between the surrounding and the system will become an externally irreversible heat transfer. So, what it means is that when we say that quasi equilibrium, we mean internally reversible, but there is no guarantee that it is externally reversible. However, when we say reversible, we mean reversible in all respects, externally, internally, whatever. So, if once we say that it is a reversible process, we automatically ensure that it is an internally reversible process. So, once we write this as TDS, automatically we can write this as PDV with the understanding that there is no other form of work other than moving boundary work, that we have to be careful. So, under all these restrictions we can write this, but once we have written this, this becomes a very powerful thermodynamic expression. This powerful thermodynamic relationship is powerful because this now involves all exact differentials. See, when we write del Q or del W, all of you understand that these are inexact differentials because these depend on the thermodynamic path. To find out the work done as the system undergoes a change of state from state 1 to state 2, you have to write, you have to basically know the thermodynamic path by which the system has gone from state 1 to state 2 to find out the work. Similarly, you need to do that to find out the heat transfer, but to find out the change in volume as the system goes from state 1 to state 2, only the final volume and initial volume is important and not how the system has changed its volume. So, volume therefore is called as a point function, or the differential of volume is called as exact differential, and volume is a thermodynamic property. So, a property is something in thermodynamics which the differential of which can be expressed as exact differential. So, if its differential cannot be expressed as exact differential, that is not a thermodynamic property. So, you can see that in this expression all differentials are expressed in terms of exact differentials, right, because all differentials are expressed in terms of exact differentials. This is a property relationship, and the property relationship means that this does not restrict any process, but here there is a very important conceptual issue. You may argue that just now we said that this is valid for a reversible process, and now we are saying that it is valid for any process. So, where is the conflict? There is no such conflict. We have to understand the inner meaning of this statement very carefully. So, let us say that we want to use this expression for getting a change in entropy. So, to get a change in entropy, what you need to do? You need to integrate this. That integration has to be executed along a reversible path. Like, let us draw a schematic to understand this. Let us say this is any thermodynamic plane, this is state 1, this is state 2, this is let us not draw any process, just states 1 and 2, state 1 and this is state 2. The system, let us say, has undergone an irreversible process by which it has changed its state from state 1 to state 2. Okay. Dotted line, because you know intermediate states are not well defined, it is an irreversible process. Now, you want to find out the change in entropy. So, what you can do? You can construct a hypothetical reversible process between state 1 and state 2, right. Integrate the TDS expression along that reversible path, and once that integration is carried out, this history is no more important because it is a point function that S2 minus S1 will be same for the original dotted line process. That is what we mean by this, that this is valid for any process. The integration has to be carried along a reversible path, but once that integration has been carried out, the resultant change can be expressed or utilized to evaluate the change in entropy for any process. That is what we mean. So, what we will do is we will write, let us come back to this expression in place of okay. Now, the next step is very simple, you know, I is equal to H minus PV. So, this will be dH minus PdV minus VdP plus PdV. So, that PdV gets cancelled out. So, dH minus VdP. So, in place of dH we will write TdS plus VdP. Okay. Now, again see, we have tried to get rid of a problem by trying to express things in terms of measurable quantities, but apparently we have entered into a deeper problem by expressing it in terms of something which is perhaps the most difficult thermodynamic quantity to measure, the entropy. So, the situation is that we now need to express the entropy in terms of measurable parameters. So, just in the same spirit as which we expressed H as a function of T and P, let us express S as a function of T and P. So, we can write ds this plus okay. Now, we can express this del S del P at constant temperature in terms of what? We can express this in terms of measurable thermodynamic parameters by using one of the 4 Maxwell's relationships. Okay. So, this is the Maxwell's relationship that we will use. Remember again, like, because microfluidics is a multi disciplinary subject, I mean you will find that like same scientists, these physicists were so strong that they contributed in several ways to different branches of physics, and those contributions are many times common or important in several branches of modern day science, like microfluidics for example. So, Maxwell on one hand discussed about 4 thermodynamic expressions or relationships, this is one of them. On the other hand, Maxwell has 4 equations in electromagnetic theory, and we will discuss about those 4 equations. Those are also Maxwell's equations and very famous equations, and we will discuss those in the context of magneto-hydrodynamically actuated flow in microfluidic devices. That is just a passing remark, not exactly relevant to what we are doing today. So, therefore, now let us do the simplification. You can write in place of dH TdS plus VdP. So, that means this is T del S del T at constant pressure dt